I was reading about this fascinating real-world geometry puzzle.
Oh, yeah.
Imagine you own a museum, right? And it's this really weirdly shaped, non-convex building. And you need to figure out the absolute minimum number of security guards to see every single spot.
Ah, you've stumbled right into the art gallery problem.
Eh.
It's like the perfect entry point for geometric algorithms.
It seems so practical, so what's the answer?
For a simple polygon with, say, yin corners, the solution is surprisingly elegant. You need, at most, the floor of n divided by 3 guards.
Wait, n divided by 3, that's so specific. Why that exact fraction? It feels like there's a key there, not just a guess.
It is a key. The whole insight comes from, simplifying the problem. You can break down any complex polygon into a set of simple triangles. It's a process called triangulation.
Okay, so you have a bunch of triangles.
Exactly. Then you color the corners, the vertices, using just 3 colors. You'll find that one of those color groups is always the smallest. Put your guards on just those vertices, and you've covered the entire gallery.
That is beautiful. And I think that's really our mission for this deep dive, to get into the elegant math and these surprising speed optimizations that make really complex spatial problems solvable.
And it often starts with the most fundamental concept.
Yeah.
Convexity.
Right. A shape is convex if you can draw a straight line between any 2 points inside it and the line stays completely inside.
Perfect. So if you have a scatter plot of points, the convex hull is the smallest convex shape that contains all of them.
So it's basically like snapping a giant rubber band around all the points on a board. That boundary is the hull.
That's a great analogy. And finding the points that make up that rubber band boundary is a classic problem.
But the obvious way to do it, just checking every possible combination of points, is incredibly slow.
Oh, it's terrible. You end up with algorithms that are like ON cubed or even ON to the 4th. It just doesn't work for modern data sets.
So then the innovation starts. I read about this idea of output sensitivity.
Yes, with Jarvis's wrap. The brilliant idea was that the algorithm speed shouldn't just depend on how many points you start with, but on how many points are in the final answer, H.
The number of vertices on the hull itself.
Exactly. So Jarvis's wrap gets you ON. If you have 1,000,000 points but only, say, a triangle for a hull, it's incredibly fast.
But that's not even the end of the line, is it?
Not at all. The pinnacle is Chan's algorithm. It cleverly combines the best parts of earlier methods to hit the optimal worst-case time of ON log H. That's pretty much the mathematical speed limit.
That kind of progress is just staggering. But what about more compliant problems like intersecting routes on a map? You need more than just a hull.
You do. When you need to ask questions like, is this specific location inside this zone? Over and over, you need more structure. That's where something called the trapezoidal map comes in.
Okay, trapezoids, how does that work?
Imagine taking your map, and from every single corner of every line segment, you just drop a perfectly vertical line down.
Ah, so you're partitioning the entire plane into these simple, easy-to-analyze trapezoids.
Precisely. And if you build this map using a clever method called randomized incremental construction, you get unbelievably fast query times. We're talking O log n.
So finding a point on a huge map becomes almost instantaneous.
It does.
Translating these really sophisticated geometric and probabilistic ideas into software that actually works, that's reliable and fast, that takes some serious expertise.
It absolutely does.
And that's actually a great place to mention our sponsor, EmberSilk. If your organization needs help turning advanced AI concepts into reality, whether it's for AI training, automation, or custom software development, EmberSilk provides that deep knowledge. You can check them out at embersilk.com for your AI needs.
And that push for speed is just relentless. For simple polygons, building that trapezoidal map can be done in what's effectively linear time. ON, log star, n.
Log star n. Okay, you have to explain that little star, the iterated logarithm.
Right. It's a function that grows so incredibly, absurdly slowly that for any number you could possibly write down, log star of that number is like 5 or 6.
So for all practical purposes, ON log star n is basically just ON.
It's as close to linear time as you can get.
Yeah.
It's an inspiring testament to progress, showing that we can solve these immensely complex spatial problems almost instantly.
It really is. It feels like we've sort of mastered 2D geometry, but the next frontier has to be scaling that elegance up.
Into higher dimensions.
Exactly. Applying these same principles to, self-driving cars, navigating 3D space, or analyzing complex 4D spatiotemporal data, the next great challenge is finding that next exponential speedup for high-dimensional geometry. That's the future.
A fascinating path forward indeed.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.